Hi there, welcome to Raelene Math. We're continuing on in our video series on the Pythagorean Theorem. We've just proven the Pythagorean Theorem, and now I'd like to draw your attention to a set of three whole numbers which make up a right triangle, or which satisfy the Pythagorean Theorem. Such a set of numbers is called a Pythagorean triple. One simple example is the set of numbers 3, 4, 5. The largest number is always the hypotenuse. These three numbers satisfy the Pythagorean Theorem because when you square 3 and square 4 and add them together, the result is equal to the hypotenuse squared. So 3 squared is 9, 4 squared is 16, and 9 plus 16 is 25, which is what 5 squared is equal to. Another example is the Pythagorean triple 5, 12, 13. So those could form three whole number sides of a right triangle, and another way to show that these three numbers satisfy the Pythagorean theorem is to square the first two and add them together, which gives us 169, and then to square the hypotenuse, which is also 169. And here we're just confirming that the square root of 169 is indeed 13. So it's worthwhile to know a few sets of Pythagorean triples. Here's 5 to get you started. Another thing to consider is that any time that you double or triple or scale all of the numbers of one Pythagorean triple, you automatically get another Pythagorean triple. We'll see more about this in our series on slope, rates, and similarity. Let's now apply the Pythagorean theorem to come up with the distance between 2 points in 2 dimensions. Here we have a point located at -5, 4, and a second point located at 3, -2. We can draw a line between those 2 points, which would form the hypotenuse of a right triangle. When we sketch that triangle, we may want to label a third point here, C, which is going to be in the same vertical line as point A, and therefore having the same x-coordinate at -5, and in the same horizontal line as point B, so it has the same y-coordinate. Then we could call the hypotenuse, normally C, we could call it distance and give it the subscript of AB, showing that it's the distance between those points. We can come up with the base, which is the horizontal distance from point C to B, so we're increasing from -5 to 3, and we get that by subtracting the bigger number minus the smaller number. We see then that the base is equal to 8. Similarly, we can come up with the height or the altitude, which is going to be A, given by a change in the y-coordinate. We take the bigger minus the smaller, and we end up getting that the altitude is equal to 6. A moment ago, we just saw that there is a Pythagorean triple. One of them is 3, 4, 5, and if we double all sides of that triple, we get 6, 8, and 10. Since the non-hypotenuse sides are 6 and 8, the hypotenuse or distance is automatically going to be 10. But we can use the Pythagorean theorem to confirm that. So the Pythagorean theorem starts off by saying a squared plus b squared equals c squared. And when we substitute the numbers in, we see that a is equal to 6, b is equal to 8, and c is given by the distance between the points a and b. So 36 plus 64 is equal to the distance squared, and therefore distance squared is equal to 100. Taking the square root of both sides says that the distance is equal to the square root of 100, which is 10, which confirms what we knew from using the Pythagorean triple. Now this was just a lucky case, it doesn't always work. But it is nice to see a relationship between the smaller Pythagorean triple of 3, 4, 5 and this larger Pythagorean triple of 6, 8, 10. In fact, if we take this smaller triangle and we scale it in proportion, we see that we get the similar triangles of the blue one and the green one. In other words, we can fit 2 of these green triangles into this blue one. There's one 3, 4, 5 right triangle and the other 3, 4, 5 right triangle, where all of these points here, A, B, and another point, lie on the same line. Again, we'll explore this relationship more in the video series on slope, rates, and similarity. Let's now generalize this result to the distance between any 2 points in the xy plane. Here's a point A, which I will label with coordinates x1, y1, and another point B with coordinates x2, y2. There's a formula that a lot of people memorize, but I want to show how this formula comes about by just applying Pythagorean theorem. When we want to find the distance on a line segment, we imagine the line segment forming the hypotenuse of a triangle. I'm going to drop a vertical line down and a horizontal line across so that we automatically have a right angle. And I'm going to give the point C here as having the same x-coordinate in the vertical line as point B, and the same y-coordinate from the horizontal line as point A. Now you could draw your triangle this direction as well. It doesn't make any difference. It's going to give the same three sides of the triangle. I like to draw it like this because it leads to where we go later on in trigonometry when we measure our angles in standard position. So we see that this hypotenuse then is the distance between points A and B, and that's what we want to calculate. So we need to come up with the height or altitude, which is going to be an increase in the y-coordinates from y1 to y2. And so when we want to come up with that positive distance, we subtract the bigger minus the smaller. Similarly, we want to come up with the base, which is the change in x-coordinates from point A to point C. And to do that, we take the bigger x-coordinate minus the smaller x-coordinate to give us the positive distance for the base. Then Pythagorean theorem tells us again that a squared plus b squared is equal to c squared, or base squared plus altitude squared equals hypotenuse squared. The base squared then is x2 minus x1 all squared. Then we take the altitude and we square it, which is y2 minus y1 all squared. And instead of c for the hypotenuse, I'm just going to replace it with distance, or distance from point A to B, and then we square that. Lastly, we isolate the distance by taking the square root of both sides. And this is how we can come up with the formula by understanding the geometry and the relationship between Pythagorean theorem and the coordinates x1, y1, and x2, y2. Check out the next video in the series to see how the Pythagorean theorem is related to the equation of a circle, a fundamental trig identity, and the magnitude of a vector. If you like the video, click like, subscribe to the channel, and I'll see you next time. Thanks for checking out Raelene Math.